Welcome back. So at this point, you should have completed our work with lab number 1, looking at position and velocity versus time graphs, and done the practice with working with those graphs. And now what we need to do is incorporate a few formal definitions of things here in physics that will be important for the remainder of this year and beyond. It's also something that's really important in math as you continue studying in math. You may have learned about these things or you may not have, but it's really important that we get a good foundation here. And what we're going to talk about is what's called a vector quantity and what is called a scalar quantity. And for our motions so far, we've looked at position and velocity versus time graphs, and we need to understand where are those quantities and when do we use vectors, when do we use scalars, how are they different, how are they connected. Alright, so let's go ahead and get started here. So first thing, we need to talk about scalar quantities. Scalar quantities are something that have only magnitude. And magnitude isn't really something that you talk about until you get to physics, so it's important to give that a bit of a context. What we mean by magnitude for math terms is something you can think of as the absolute value only. So in math, let's say you have the number -4. What we're talking about with magnitude would be just the number part of that, which would be 4. It's sometimes more helpful, though, to talk about it in terms of real-life things. So let's say you're driving your car. You're driving your car at 25 miles per hour. That's what the odometer shows. This would be an example of a scalar quantity, because all we have is a number, as well as some units. If I said that we were driving 25 miles per hour north, then you've given it an additional piece of information. You have given it a direction. Direction is not part of something that is scalar. So scalar would be 25 miles per hour. It could be a distance, like 20 miles. It could be a measurement, like 20 grams of mass. It could be a temperature, 70 degrees Fahrenheit. There are all sorts of different things that are scalar. The big important takeaway is that there is no indication of direction. So then the alternate thing we have are things that do have direction, which we call vector quantities. Vector quantities have that number, so as we just talked about, 25 miles per hour. But in addition to that 25 miles per hour, we're given some indication of direction. 25 miles per hour left, 25 miles per hour right, up, down, north, south. Anything that indicates direction makes this a vector. Now, how we indicate direction differs based on the situation. So oftentimes we use a plus or a minus. Depending on the scenario, that plus or minus indicates something different for direction, right? So if we have a two-dimensional coordinate system here, we usually indicate that positive could be positive in the y direction or positive in the x direction, or maybe you've got a z direction. You might say north, south, east, west. So maybe not necessarily positive or negative, right? Saying that you have a temperature of -25 degrees Celsius isn't a direction. That's just on sort of an absolute value scale. But examples that we've looked at so far are when you're moving with both a certain rate, a speed, and direction. We call that velocity. We're going to talk in just a moment about what's called displacement, or how far you go from your starting location. That would be another example of a vector quantity. And what we'll look at soon would be force, momentum. So for those who have taken physics before, this should sound familiar. You should remember these things. For those who have not, it's just really important to always cue into the fact that some things have direction and some don't, and it changes how things interact and what they produce when they interact. The last piece to remember then is that positive and negative here do not work as they often do in math, in the sense that in math, positive and negative's on a number line, and it's tell you whether something's greater or less than something else. In this case, as we've seen with the moving man, positive and negative tells us direction. All right, let's go ahead and keep on moving. So some example of vector and scalar. Well, if some of you guys remember this fun character Victor from Despicable Me, what does he say? I commit crimes with direction and magnitude. Right, so that's a reference to this vector idea. But Let's take a look at some other examples of vector versus scalar. I have just a brief video here to share with you all. So what we need to do today is take this idea of vector and scalar and apply it to two important pairs of things in motion. The first pair of things is distance and displacement. So distance and displacement, let's first give these things formal definitions. So first, the symbol. There are many symbols for displacement. It all depends on your coordinate system. If you're moving just left or right, we use this delta x. If you're moving just up or down, we would use this delta y. Make sure it's clear that's a triangle. In your textbook, it often uses delta s. And we use delta s for an example like this, where let's say I have a coordinate system with the origin mapped over point A. This contains both an x and a y coordinate, so I would use s to represent the fact that this is in two directions. Sometimes we want to use r. So when you learn about the unit circle and we talk about r vector is a special type of vector we'll talk about later in the year. All of these different symbols can represent displacement. Remember that this triangle indicates change in, which you often see in chemistry, right? You use this delta for a variety of different things, and we use it in physics too. It means change in. And one important thing to note here as we start to move more through motion is change in is generally considering things over a long time. Sometimes we're going to talk about instantaneous change, and that'll be the foundation for derivatives in calculus. But for now, we're talking about more of a long-term change. So this would literally mean change in x, or change in x position. So we can write that as a definition. So to write this out would mean for this equation, delta x is x final minus x initial. So this little 0 here indicates, it's called naught usually, like N-A-U-G-H-T, I think. Now I'm second guessing myself, but it's a symbol used for initial. So we would have an initial position, let's say in this display here it'd be 0 meters, and let's say I move a total distance along this path s of 5 up here. We'll talk more about this later, but for now my change would be 5 minus 0, or 5 meters. That would be change in position. This contrasts with distance. Distance, we use the symbol lowercase d, and notice how I have these little sort of weird half arrows above everything for displacement, but I do not have it for distance. This little half arrow indicates that something is a vector quantity. Now sometimes, like in your textbook, you won't see the half arrow. It will be bolded to indicate a vector quantity. I can't really bold something, so we use this little half arrow. Distance is a scalar. Distance is defined to be the total sort of path length that you travel. And I find the best way to explain that is to think about the odometer in your car. That numbering never goes down. As you drive your car and you move, it always counts up because it's counting the total path length you have traveled with your car. The only way to measure distance would be to have something like a ruler or a measuring tape where we could put it all along this path 3 and record what is the total distance when we travel that whole pathway there. Let's look at another example of distance versus displacement. Helpful example is to look at this shape here that's kind of like a track you'd run on for track and field. In this display here, if I go from A to B, it's listed as 100 meters. This would be an example of distance, d. But my displacement is from my initial position to my final position. That is listed as only 50 meters. So displacement doesn't always accurately represent how much you moved. It's only representing how far are you from your original location. If I continued to go around the circle, what would my total distance be? I've now moved another 100 meters, so my distance here would be 200 meters. Whereas I've returned to my same spot, so I would have a position of A as my final minus a position of A as my initial, meaning that my displacement would appear to be 0. I did move, but for displacement, my change in position, it's 0. What we'll do now is work through a few example questions here. If you're pretty comfortable with distance and displacement, perhaps because you've taken a year of physics already, feel free to skip ahead. Otherwise, let's work through some practice. We have a football player who starts on the 40-yard line, and he runs to the 10-yard line. What is his displacement? Remember that displacement is final minus initial. So if my final is 10 and my initial is 40, then my displacement is a negative 30 yards. Remember that that negative indicates the direction in which I've moved, so that's important for displacement. My distance, on the other hand, is simply measuring that I moved 10, 20, 30 yards, so my distance would be 30 yards with no indication of direction. Let's look at another example. Well, I sort of jumped the gun on that. But we just talked about this, right? What's the distance if I go from 40 to 10? It's a positive 30. All right, now we have a football player who starts at the 20-yard line, runs to the 50-yard marker, and then cuts back to the 30-yard marker. We're asked, what's the total displacement? Take a moment to come up with your own answer. Okay, so remember it is final minus initial. So that would be a displacement of 10 yards. We're asked now, what is the total distance when we go from 10 to 50 and then 50 back to 30? Now I don't care about direction. I care about just adding up all the pieces. So I have 30 for my first movement, and then 20 for my second movement gives me a total distance of 50 yards. That would be my answer. Another example. So we start with the player at 10 yards, or is it? Careful reading, right? 10 yards deep, so this is 0, this would be at negative 10 yards, and then runs it to the 35-yard line. We're asked, what's the initial position? So it is not positive 10 yards. It is instead one of our negative 10 yards. Now we're asked what's the displacement. So remember, it is final minus initial. So this is where things can get tricky. Final is 35 yards minus an initial of 10 yards turns that minus a negative into a positive to be 45 yards. So we started at negative 10 and we have a positive displacement of 45 yards. Careful. All right, now we ran a 400-meter event in track, and we started in the first lane. We start on the finish line here and run one complete lap. What is our displacement? What do you think? We start and end at the same location, and so nothing else matters except those two bits of information. All right, now let's talk about another question. Is it possible for distance and displacement to have the same value? Statement A, yes, they always are. So we know that's not true, right? We've seen examples of that where if I go around in a full circle, then they wouldn't be the same. Statement 2, yes, only if they don't change direction. So that can be pretty tempting, right? If I move to the right 20 meters, then my displacement and my distance are both 20 meters. But what if I go the other way? My distance was 20 meters, but my displacement was negative 20 meters, so it can't be that. And that eliminates C as well. So the statement is correct if I say yes, they can be the same. If I move in the positive direction and I don't change directions, then my distance and displacement would be the same. Say I take a road trip from my house to some destination. When I get to that destination, how does my displacement compare with my distance? So my displacement and my distance have an important relationship here where if I went on a straight path to that other location, then both my change in position and my distance could be the same. But my displacement couldn't be greater. And if I went on a zigzaggy path, I would have a greater distance but the same displacement. So the displacement can never be greater than the distance. So anything that talks about greater than has to go away. And it's not always equal to. It could either be equal to, in very specific cases where I move in the positive direction the whole time and I don't deviate, or it will be less than. All right, now an example. We walk the dog. Dog moves at 2 meters per second. When I'm 200 meters away, my dog is so excited that it takes off running straight towards the water at a constant 10 meters per second. Once reaching the water, it turns around and runs back to me. Then back to the water and back to you. Back, 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 back. If I maintain my speed, how far will the dog have run? So let's talk about how we want to handle these things. There are a few different ways that we can do it. My general sort of rule of thumb is to draw velocity versus time graphs. We have to make some assumptions here, right? The first assumption we make is that the dog instantly changes direction and runs back and forth, back and forth, back and forth. Otherwise, this would be pretty complicated. For me, I am at 2 meters per second. I'm not told the direction except sort of towards the lake, so we're going to call that positive, and that stays the same the whole time. What we want to know then is how long does it take me to travel the 200 meters? So in terms of speed, what we generally say is that speed, and I'm going to make a stipulation here that we'll talk about more soon, average speed is the distance that you travel divided by your time interval. So to find my time interval, we're going to take my distance that I need to travel, 200 meters, and divide it by my speed of 2 meters per second. And when we do that, I obtain 100 seconds. Right. We're then asked, if I maintain that speed, how far will the dog have run by the time I reach the lake? Now we're asked how far. So what we're asked here is not a displacement. We're asked what is the total distance that the dog travels. So then this makes things pretty simple to handle. Right? In that same amount of time, the dog is going back and forth, back and forth, back and forth. Now, technically, the dog would start with a velocity of 10, right? And once the dog has reached that distance, 200 meters, in about 20 seconds, the dog would then turn around and run back. But the big thing is just overall that dog is running at a 10 meter per second speed over and over and over and over until all the time is run out. So the dog's just going back and forth, back and forth, back and forth. We're not worried about that time it takes the dog to change speed. So if it takes me 100 seconds, then the dog will be running at 10 meters per second. And what we're going to do is move this time over the other side so we can say the distance is that 10 meters per second times 100 seconds. And so that dog will move a total of 1,000 meters. Now that we've talked about velocity and speed a little bit, let's go ahead and talk about how we would define these two things and what their equations would be. So first, velocity. Velocity is the vector quantity because it has both a magnitude and a direction. So a velocity is defined in this way. Average velocity is defined to be your change in position per some time interval. And it's really important in your notes that you highlight this average velocity statement. Right? Average velocity is over long time intervals. We also have what's called instantaneous velocity. So if you have seen derivatives already, what we would call v instantaneous is equal to the derivative of position with respect to time. If you've not seen calculus yet, don't worry about it. We'll talk about it during the school year. But I just state it so that you get a sense of why I'm highlighting this as average velocity. It is not instantaneous velocity. It is average velocity over that whole time interval. So notice how it depends on a vector, and that's what makes it a vector quantity. When we take a vector and divide it by time, which is generally considered to be a scalar quantity, we obtain another vector. The alternative is average speed. Speed is the distance you travel divided by your time interval. So notice both of these have this time interval here. It's a bad habit to write d over t. They often do that in middle school. Do not get into that habit. It is not one individual time. If we're talking about one individual time, we're talking about what is instead an instantaneous speed. So instantaneous speed, the symbol is a v without the vector symbol. And v instantaneous then would actually be the absolute value of the derivative of position with respect to time. So if you think about on a position time graph, we're talking about for this position time graph, what is the magnitude or the absolute value of this slope? So maybe we have a negative slope, but for instantaneous speed and average speed, we'd be talking about something to do with the absolute value of this slope. All right, let's go ahead and continue. Normal written definitions here. So remember that velocity is a vector quantity, and so it depends on the change of position, which is also a vector quantity. And we have magnitude and direction. There's both magnitude and direction for velocity, so if I'm moving at 25 meters per second, I need to specify which way I go. Whereas on the car, when we're given that reading of that speed, 25 meters per second, without the direction, that then is a scalar quantity. It is the magnitude only. Make sure we talk about units. Units can come from the equation, but do not use units to develop an equation. So if average velocity, remember we can't really tell bold, so we'll put that on. If average velocity is change in position over change in time, the units in base SI units that we will always use is meters per second. You could say kilometers per hour, miles per hour, all of those things will be valid, but those aren't the base SI units that we want to be using. Question. If my displacement is positive, so in this displacement over change in time, this part is positive, what is the direction of my velocity? So the key connection is that if the left side is positive, as determined by the change in position, then the velocity must also be positive. Their signs must always match. A football player who starts at the 40-yard mark and runs to the 10-yard mark in 5 seconds. What is the average velocity? So remember, that is change in position over change in time. So the final position is 10 yards, and the initial position is 40 yards. So I need to subtract that, and it takes 5 seconds. So then we would have a negative 30 yards in 5 seconds, or a value of negative 6 yards per second. So this would be the average velocity. But now average speed. Remember that average speed is defined as the distance over the change in time. So this time my distance, I don't care about direction, is 30 yards in 5 seconds. And so this time my speed is 6 yards per second on average. Not instantaneous, but average. Speed and velocity are noticeably different. So this time the player starts at the 20-yard line, runs to the 50, and then runs back to the 30, all in 10 seconds. What is the average velocity? So this time, remember, change in position over change in time. This time we went from 20 to 50 and then back to 30. We only care, though, about the beginning and the end. So the final was 30, the beginning was 20, and this took 10 seconds. So I have 10 yards per 10 seconds. And so the average velocity was 1 yard per second. Would be speed. In this case now, in going from 20 to 50 and then 50 back to 30, the total distance is the 30 yards plus the 20 yards. Not worried about direction, and that all took 10 seconds. So for speed, instead of being 1 yard per second, now we have 50 yards in 10 seconds. And so this time the average speed was 5 yards per 1 second. Totally different from the average velocity. We're comfortable with this idea of magnitude. If a dog has a velocity of negative 4 meters per second, what is the magnitude of the dog's velocity? Remember that magnitude is like absolute value, so it is the number without the direction. It is 4 meters per second. Question that might have an answer that you wouldn't expect. You go on a 100-mile long road trip. For the first 50 miles, you were going 60 miles an hour, and for the last 50 miles, you were going 80 miles an hour. What is your average speed, assuming no pit stops? Pause the video, take a moment to think through your answer. So I'm going to assume now that you are ready to talk about the answer. If not, try and think through it. Did you pick the answer B, 70? If so, that's unfortunately not the right answer. This would be the right answer if we spent the same amount of time going 60 as we did 80. This is the example of a question where you have to be really careful about the definition of what is the definition for average speed. The definition is the total distance traveled divided by the time. Now we know the total distance traveled, that's 100. The thing that we don't know is the time. So we need to find the time. For the first time interval, when I'm going 50 miles an hour, the time is equal to the distance divided by the average speed. So that would be 50 divided by 60. For the second one then, the time would be 50 miles. Let's make sure I put in units. Miles per hour. Divided by 80 miles per hour. So my total time is 5/6 plus 5/8. Right? This is my delta t, is 5/6 plus 5/8. 1.458 hours for the time it takes me to get there. So if we take this distance of 100 and divide it by 1.458 hours, when we plug that into our calculator, we obtain an average speed of 68.6 miles per hour, which is close to 70, but it is not 70. The reason being, if we want to think about this conceptually for a little bit, it takes me much longer, right, this 50 out of 60 of this 5/6 of an hour to travel the first 50 miles. And so I spend more time at that lower speed than whenever I do the second part of the motion, where it only takes me 5/8 of an hour to travel the 50 miles. So my average speed will be less than the middle of those two. It will be less than 70. Another example here. So now we have an automatic speed trap that is set up with two sensors, and the speed limit is 30 miles per hour. But you hit the first sensor strip going 60 miles per hour. What is the maximum speed you need to slow down to before hitting the second sensor strip in order to not get a ticket? Think about your answer for a moment, pause the video, and then we'll discuss. So I'm going to assume that you've thought about this a little bit. The first answer that folks would think of is, oh, well, if I go down to 30 miles per hour, then that means that by the end of the sensor, I'm going 30 miles per hour. I'm within the speed limit, right? But the problem here is that when you start at 60 and then you move while slowing down to 30, your speed is always greater than 30. So that would not work for us here. That would be a problem. It's, I think, easier to talk about why C isn't the right answer either. We'd want to come to a complete stop, then speed up to 30 miles an hour. Well, if we do that, that will technically get us to a speed less than 30 miles an hour, right? I mean, we're going to go from 60 to 0, and you could sit there for a long time and then speed up to 30, and you'll be less than 30, but it's not the maximum speed. Instead, it's somewhere in between 30 and 0, but we need to hit less than 30 miles per hour in order to have this much higher than the speed limit, 60, be balanced out by something less than 30 so that they come together. Now remember that we define the speed as distance divided by change in time. So it really depends on how quickly you slow down to your new speed here, something less than 30. Let's say you go 20. So that this 20 miles an hour is weighted more heavily. Talk about how to solve motion problems, and this will be really important as we move further along in the unit. The key is that you must always set up and use a velocity versus time graph. So let's say that you are driving a car and you are moving at 10 miles per hour. If I were to make a velocity versus time graph, I would say that you are moving at 10 miles per hour, and we'll say you're moving 10 miles per hour in the positive direction. So I have this constant velocity. Let's say I want to know how far you go. Right? In 1 hour, so let's make our time interval here hours. In 1 hour, moving at 10 miles per hour, I'm going to move a total distance of 10 miles. So because I move 10 miles per hour times the time of 1 hour. So I'm multiplying this one piece, my average velocity here, times my time. So we have V average times delta t gives me both my distance and my displacement in this case. Now we're multiplying this time and this average velocity together. And so what I want you to notice is that we are multiplying a height times a base, and what you are finding is the area of this part of the graph. If I do that for another hour, so I'm now from hour 1 to hour 2, during that second hour I move again another 10 miles, and so the total area of these put together would be 20 miles. Now let's say instead of continuing like that, I instantly stop, I break the laws of physics and I instantly stop, and then I move backwards in the other direction at a negative 10 miles per hour. This time, for that first hour, I am multiplying a negative 10 by a 1, and so I would have an area of negative 10. My displacement now would be this 20 plus this negative 10 gives me a new overall area of positive 10. Whereas my total distance would be the 20 plus the 10, regardless of direction, for 30. So we had 20 minus 10 equals 10, and 20 plus 10 equals 30. So for another hour, if I now have this other area that is negative 20, and I add that with a positive 20, my new displacement is now 0. So the key thing here that I want you to take away is that the displacement on a VT graph equals the area from the line to the x-axis. So from the line to the x-axis. Usually people write area under the graph or under the line. I feel like the word under can be confusing. It's the area between your actual data and the x-axis. What will soon be called in your calculus class the either integral or antiderivative. But for now, we're just going to be working with rectangles and triangles, and so it's really just geometry and algebra. Don't worry about the fact that it's calculus until we need that a little bit further along. For all the stuff we do this unit, it will instead be simple geometric shapes. Do is model this process with problem number 1 from your practice problems, which is problem number 1 from night chapter 2. So we're told that one person leaves LA at 8 a.m. to drive to San Francisco 400 miles away. He travels at 50 miles per hour. So we're assuming he's just moving straight. Maybe this is what Elon Musk's tubing system underground, and you can just move straight. Beth leaves LA at 9 a.m. and drives 60 miles per hour. And we're asked who gets to San Francisco first, and we were asked how long does it take how long does the first person have to then wait. So you could do some calculating right away with equations, but that's not what I want you to do. Instead, what I really want to emphasize instead is making velocity time graphs. And let's go ahead and do that. Say that this time of 0 is at 8 a.m. And we're told this person's moving from LA to San Francisco, which I believe was 400 miles away. And we were told the speed was 50 miles an hour, but let's just check and make sure. So 400 miles away, 50 miles per hour at a steady rate. So first I'll just mark a point. Let's say this is 50 miles per hour. And that's a steady rate for those 400 miles. So remember we said that the area below the graph is the total displacement. And it's the same thing as distance as long as the direction doesn't change. So we could think about how long does that take. And so this area under here represents 400 miles. So to get this area, right, we'd have to have some height, in this case 50. So we have this average velocity of 50 times whatever that time interval is, has to equal the displacement, and that displacement is 400 miles. So to solve for time, I'm going to divide by 50 on both sides. And when I divide by 50 miles per hour on both sides, I get that the time interval would be 8 hours. So this would end somewhere over here. Let's just pick an arbitrary spot to be 8 hours. And the area underneath that is equal to 400. So for the second person, let's use a different color, that second person waits an hour before leaving. So their graph would start out with a velocity of 0. The person then moves at 60 miles an hour. So now we're going to have this be up here. And the key is that the time may take something different, but the area, whatever that is, and let's leave it open for now, this new area here also has to equal 400 miles per hour because we have the same, 400 miles because we have the same start and end point. So this time we have this new average velocity times that time interval is equal to that same displacement of 400 miles. So this time this is 60. So the new time interval here is going to be 400 miles divided by 60 miles per hour. So 400 divided by 60 is roughly, 6 2/3 hours. So this person, if they leave at 9, they're an hour behind, but it takes them at 1 1/3 hour less to get there. So that means that they catch up and they have that 1/3 hour where they're just hanging out. So our answer then would be 20 minutes of waiting. And it's going to be the second person is there first. Right, so I hope this was a helpful illustration about how you can model movement on velocity time graphs. You can technically do it on position time graphs too, but it's important to use velocity time graphs because soon we will have not constant velocity, and we want to be able to incorporate the acceleration piece into this too. Thank you very much for watching. If you have any questions, feel free to send me a message on Remind or an email, and I hope you have a rest of your great day. Hope you have a great rest of your day.